Let us discuss the nomenclature of coordination compounds. But before we start the nomenclature, we discuss two very important terms. One is how to calculate the oxidation state of metal in a coordination compound and how to find the coordination number of a metal in a coordination compound. So first we will discuss how to calculate the oxidation state of metal in a coordination compound or in a complex ion. And I am using this abbreviation OS for oxidation state. Now let us take this example K4FeCN6. This is called potassium ferrocyanide. Our aim is to find the oxidation state of iron. So to calculate the oxidation state of the metal, we should know the charge carried by different ions in a coordination compound. For example, we know that potassium carries a charge of +1 and there are 4 potassium atoms. So we write 4 into +1. We assume the oxidation state of iron be X, so plus X. And we also know that Cn carries a charge of -1 and there are 6 cyanide ions in this case. So we write 6 into -1 and the whole complex is electrically neutral. It does not carry any charge, so equals to 0. And then we calculate X, X comes out to be +2. And we write this oxidation state of metal in a coordination compound in Roman numerals. So the oxidation state of iron in potassium ferrocyanide is +2. Now second example is this. It is cobalt, NH3(6) and Cl3. Now suppose our aim is to find the oxidation state of cobalt. So we assume the cobalt to be X and there are 6 ammonia present as a ligand, and ammonia does not carry any charge. Ammonia is a neutral molecule, so it's 0. Then we have a 3 chlorine present and each chlorine is carrying a charge of -1, so 3 into -1, and the whole coordination compound is electrically neutral, equals to 0, so X is +3. So in this coordination compound, oxidation state of cobalt is +3. Now we take one more example. This is FeH2O(5) Cl, and this complex is carrying a charge of 2 positive. So it's a complex cation. So again our aim is to find the oxidation state of iron. We assume the oxidation state of iron be X, water is neutral, so 5 into 0, chlorine is -1, so 1 into -1, and the whole complex is carrying a charge of +2, so equals to +2, and X is equal to +3. So in this complex also iron oxidation state is +3. So this oxidation state is defined as the charge left on a given atom when we remove all other atoms or groups in the form of ions. So oxidation state is defined as the charge left on the given atom when we remove all other atoms or groups in the form of ions. Next we define the meaning of coordination number. Now this coordination number is defined as the number of nearest neighbors. Or coordination number can also be defined as the number of atoms which are in direct contact with the metal atom. to find the coordination number, we should know the denticity of each ligand in the complex. And coordination number you can calculate as this. So coordination number is equal to summation number of ligands each with the denticity of di. So Ni stands for the number of ligands, and D stands for the denticity of the ligand. For example, this is FeCN whole 6 4 negative. Now in this case, any atom or group other than the metal in the square bracket is called a ligand. So in this case, the CN is present as a ligand, and there are 6 CN groups present in this, and each CN has a denticity of 1. So in this case, the coordination number is equal to there are 6 cyanido present, each with a denticity of 1 equals to 6. So the coordination number of iron in this complex ion is 6. This is a complex of chromium CrNH3 whole 4 En, and the complex is carrying a charge of 3 positive. Now in this case, we have 2 different ligands present. We have amine NH3 and we have ethane 1,2 diamine En. So we calculate the coordination number of chromium in this complex ion is equal to 4 ammonia. There are 4 amines present, each with a denticity of 1, plus we have 1 En with a denticity of 2. So this is equal to 6. So the coordination number of chromium in this complex is equal to 6. We have one more example. This is called NiNH3 whole twice Cl2. So our aim is to find the coordination number of nickel. So the coordination number of nickel in this complex is equal to, we have 2 NH3 ligands present, each with a denticity of 1. We have 2 chlorido, each with a denticity of 1, and this sum is equal to 4. So we can say coordination number of nickel in this complex is equal to 4. Now when the coordination number is 6, then the geometry is called octahedral. And when the coordination number is 4, then the geometry can be either tetrahedral or square planar. Now we'll discuss the nomenclature of coordination compounds. Nomenclature of coordination compounds. Now first of all, suppose these 2 examples are given. K4 FeCN whole 6. This is called potassium ferrocyanide. Now in this case, potassium is present as a simple cation, and this anion is present as a complex anion. And in this complex anion, any atom or group other than the metal is called the ligand. Now next example is this, it's Cr H2O whole 6 Cl3. Now in this case, your anion is a simple anion, but complex is cation. Again, any atom or group other than the metal in the square bracket is called the ligand. Now to name the coordination compounds, we have to follow certain rules. And the first rule is that in the naming of coordination compound, cation is always named first. Whether you have a simple cation or you have a complex cation, cation has to be named first. Now I am taking one example to explain the nomenclature. First, of cationic complexes, means the coordination compound in which the complex is cationic part. So I am taking this example Cr, H2O whole 4, Cl2 and Cl. Now in this case, this is the cationic part, and this cation is not a simple cation, it is a complex cation. Now whenever the cation is complex, so if the cation is complex, then arrange the ligands alphabetically using a prefix di, tri, tetra, etc. to indicate the number of ligands of that type present. So in this example, we arrange the ligands as this. There are 4 H2O ligands present aqua, so we write tetra aqua. So we write tetra and then we write aqua. So there is no spacing, no comma, no hyphen. Then we have 2 chlorido, so we write dichlorido. And when you arrange the ligands alphabetically, look at the first letter of the ligand, like A of aqua and C of chlorido. So tetra aqua dichlorido. There is no other ligand present, so you just write tetra aqua dichlorido. Only 2 types of ligands present in this cation complex. Then the rule number 3 is name the metal atom. Name the metal atom followed by its oxidation state in Roman numerals. In Roman numerals. So in this case, the metal is chromium. So we write first tetra aqua dichlorido, and then we write the name of the metal now, it's a chromium, followed by its oxidation state in Roman numerals in bracket, it's a 3. Then the fourth step is you have to name the anion. Now in this example, our anion is chloride. It's not a ligand, it's an anion. So we write chloride. So the name of the complex is now tetra aqua dichlorido chromium 3. This is a cationic part. And then we write the name of the anion chloride, and cation and anion name should be separated by a small space. So there is a small gap between this name of the cation and the name of the anion. So this is a complete name of the complex which we took as an example. Now we'll discuss 1 or 2 more examples like this. This is a complex of platinum, NH3 whole 6 and Cl4. So we are taking some examples where the cation is complex. So it is named as hexaamine, amine but with a double M. Then there is no other ligand present. We write the name of the metal, platinum, followed by its oxidation state in Roman numerals, that is a 4, and then we write the name of the anion, chloride. Now next example, it is a FeH2 whole 5 NO SO4. So again the complex is cation, and there are 2 different ligands present. One is aqua H2O, second is nitrosonium, that is NO. So this coordination compound is named as penta aqua nitrosonium iron, that is the name of the metal, followed by its oxidation state in Roman numerals, that is 1, and then we write the name of the anion, sulfate. So penta aqua nitrosonium iron 1 sulfate. This is also the formula for the brown ring obtained when we perform a test for the nitrate ion. Now suppose we are given this example now. It's a CO, En whole twice and SO4. Now in this case again the cation is complex, but the ligand present in this case is En, and we know that En stands for ethane 1,2 diamine. Now di is already there in the name of the ligand. In such cases we cannot use again di tri as a prefix. So now the rule number 5. If name of the ligand already includes di tri, then we cannot use di tri tetra as a prefix. In such cases, we use a prefix bis for 2, tris for 3. And also we write the name of the ligand in bracket. So if you look at the complex again CuEn whole twice SO4, there are 2 En molecules present as a ligand, so we write bis. Then in the bracket we write the full name of the ligand. This is ethane 1,2 diamine, but diamine with a single M. Then we write name of the metal, copper, followed by its oxidation state in Roman numerals 2. Then we write the name of the anion, sulfate. So its complete name is bis ethane 1,2 diamine, copper 2 sulfate. We take one more example. Now suppose you are given this. It is a Cr, NH3 whole twice, En whole twice, and then Cl3. Now how do you name this complex? So this complex is named as diamine with a double M. Then we write bis. In bracket we write ethane 1,2 diamine. Then we write name of the metal, chromium, followed by its oxidation state 3. Then name of the anion, chloride. We have one more example. This is cobalt complex, cobalt NH3 whole 5 and ONO, and the whole complex is carrying a charge of 2 positive. So we don't know the anion in this case, only the cationic part is given. So this complex cation is named as pentaamine nitrito O, because O is a donor atom in this case. Then we write name of the metal atom, cobalt, followed by its oxidation state 3. Now in this case, as the anion is not given, so we are not writing the name of the anion. We take one more example now. Suppose you are given this, K4FeCN whole 6. Now in this case, anion is complex and cation is simple. Now, rule number 6 is, when the anion is complex, then the metal ends in ETE. For example, if you have an iron present, you will write ferrate. For copper, we write cuprate. For silver, we write argentate. Some more examples. Suppose you are given gold in the anionic complex, then we write aurate. For mercury, we write mercurate. And for nickel, we write nickelate. So in this complex potassium ferrocyanide K4FeCN whole 6, this complex is named as, first we name the cation, that is a potassium. Now anion part is complex, so we arrange the ligands alphabetically. There are only one type of ligand present, CN negative, so we write hexacyanido. Then we write the metal, but not as iron, we write ferret, followed by its oxidation state, that is 2. So its name is potassium hexacyanido ferret 2. Now next example is this. This is Nessler's reagent used in the detection of ammonium ion in the salt analysis. It's named as potassium tetraiodido mercurate and followed by its oxidation state 2. Now we take one more example. Suppose you are given this Fe3 FeCN whole 6 and 2. Now suppose this is the complex given. In this case, the iron is present inside the complex ion and iron is also present outside as a simple cation. But you know, iron shows variable oxidation state, so we don't know what is the oxidation state of iron in the simple cation or oxidation state of iron in the complex anion. So first we split this complex into cation and anion form. Now in this case, the cation part is Fe2 plus and the anion part is FeCN whole 6 with a charge of 3 negative. So we follow the rules, we name the cation first. So cation is iron. And since iron shows a variable oxidation state, so you mention the oxidation state of iron. So iron 2, then your anion is complex, so we arrange the ligands alphabetically. So we write hexacyanido. Now this iron which is present in the complex anion is named as ferret, followed by its oxidation state in Roman numerals 3. So this is nomenclature of some of the important coordination compounds.